This is my lab 3 black hole. So the purpose of doing this lab is to estimate the mass of the black hole and also to calculate and model the gravitational forces on the black hole on the surrounding planets and also with the ship. And also we were supposed to find the initial velocity of the ship as it leaves the system in the planet. So our overall view of the results is that mass of the black hole is 8.923 times 10 to the 33rd kilograms. It's a lot, right? And then the velocity of the ship is negative 1.7 times 10 to the 6th and negative 3.33 times 10 to the 7th, and then 0 meters per second. So that's like the vector for the velocity to show the direction as well. So introduction. So the physics principles or fundamentals that I used in the lab is Newton's second law, the momentum principle that is shown here, which is basically delta P over delta T equals F net, and then change of momentum over change of time, and then Newton's law of gravitation, which is the gravitational constant times the two masses divided by r squared, and then velocity update formula, Vf equals Vi plus F net over m times delta T, and then position update, which is Rf equals Ri plus V average times delta T. So this is part 1. So the system is the planet and or the ship, which you can include either one, and that you can include both. And then the surroundings is the black hole. And the way I did this is through Newton's second law, and you can see that here, dp dt perp, right, or here. Basically, you just break it up into parts and then use Newton's second law, and also rearranging the laws of gravitation. And then lastly, we summed up the masses of the black hole and divided by 365 to get the average mass. And that was done in this loop right here. So this is the results for part 1. So this is the force, the net force. And then this is the parallel component, and then the perpendicular component, and then this is the mass of the black hole that we got as a result. Right? And then the sources of error, so like rounded values for the calculations, right? And then we also change, like the change in time for each step can be reduced to give more data points and increase the accuracy. So part 2 method, the way I found this is by finding both net forces on the ship, from the planet, and from the black hole. And then I added them to get the force net. And then I used the position update and velocity update to update the location. And then I repeated it until the escape speed is viable enough for it to actually escape the black hole, for the ship to escape the black hole. Or the planet, right? So we have these initial conditions: the ship speed, the ship in the x and y direction, the ship velocity, and then we have this loop. The loop gives us the overall force. So we're using the gravitational force right here, using Newton's gravitational law, and then we have the total F net of the planet on the ship and the black hole on the ship. And then we also have this to update the position and the velocities, updating position and updating velocity. And then part 2, so like the results is that the velocity of the ship was this meters per second, and then the simulation took about 135 minutes as shown in GlowScript. Source of error is that the mass of the black hole from part 1 is an average, it's not exact really, and then the different times in the smaller time intervals could also make the data more accurate. So what does it mean? So how does the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? So the net force is F parallel plus F perp, and the net force is, or F equals ma, right? So it requires mass, and it cannot be solved unless we have mass. However, change of momentum, you don't really need mass, right? Momentum is mass versus velocity, mass times velocity as a function of time. And this is the formula for dp dt using perp and parallel. So this is the parallel component, and this is the perp component, like that. And this is again F perp, parallel plus F perp. Now what if? So instead of wanting to take a quick look at a black hole and leave, you want to enter and then leave, right? You want to enter with initial velocity. So what initial velocity could you do that to enter into some kind of orbit around the black hole but not get sucked in? So it's challenging and difficult to find that, but you could do it by determining the momentum perpendicular to the net force on the ship to get that direction. And that's my lab 3. Thank you.